In this video, let's explore the fundamental principles of pressing in winemaking. Although simple in appearance, it is a decisive stage that shapes both the style and the quality of the final wine. Pressing is the process through which we extract must from fresh grapes, or wine from fermented grape pomace. When grapes arrive at the cellar, pressing can take place immediately, particularly for white wines and rosé wines. Depending on the producer's objectives, the grapes may be pressed whole, uncrushed and unstemmed, or after destemming. In other cases, when producing wines from cuvée grapes, pressing occurs only after alcoholic fermentation. In this context, the oenologist plays a key role in determining the optimal time to press, separating the free-run wine from the press wine. Pressing stands at the heart of the reception line and plays a key role in determining the efficiency of the workflow. A complete pressing cycle typically takes about 4 hours, around 30 minutes to fill the press, approximately 3 hours for the pressing itself, and another 30 minutes to empty and rinse the equipment. Under these conditions, a single press can usually handle about 3 full cycles during a standard 12-hour working day. In some situations, however, such as when grapes have already been cooled in a refrigerated storage room, allowing pressing to take place in the early morning, or when red fermented grapes require a shorter pressing program, the press may occasionally complete up to 4 cycles. For this reason, properly sizing the presses in a cellar is essential to ensure a smooth and efficient workflow. Pressing also has a strong influence on the clarity and quality of extracted must. To better understand what pressing actually extracts, let's take a look at the internal structure of the grape berry. As shown in the illustration, the berry is composed of several key parts: the stem attachment point, the waxy bloom on the surface, the skin, the pulp, the central flesh, and the seeds. During pressing, 3 distinct zones within the berry, the pulp, the central zone, and the skin, each release different compounds into the must. The mechanical action of the press breaks the skin at its weakest point, progressively releasing the various fractions of must. The pulp, called the P1 zone, delivers the highest quality must rich in sugar and tartaric acid. It is naturally low in tannins, low in potassium, and relatively low in minerals. This first fraction corresponds to the free run must released at the very beginning of the process. Next comes the central zone, or P2, which contains higher concentrations of malic acid. This portion is extracted slightly later as pressure increases gradually within the press. Finally, the skin, referred to as the P3 zone, is richer in potassium, minerals, oxidases, polyphenols, and aroma precursors. These elements are released only toward the end of the pressing program, when higher pressures are required to extract the remaining must. When the integrity of the berry is preserved, the resulting must profile follows a predictable sequence. As shown in this figure, the initial must fraction is particularly rich in sugars and tartaric acid. In the middle of the pressing cycle, the concentration of malic acid becomes higher. Then, toward the final stages, we observe an increase in potassium, polyphenols, and aroma precursors, compounds typically associated with deeper extraction. However, certain mechanical actions can compromise must quality, such as shredded stems, excessive compaction during transfer, bursting of berries, or the breaking of seeds. These issues create multiple mixing zones that increase the release of unwanted compounds, including vegetal notes, bitter or easily oxidized molecules, and astringent tannins. As a result, the quality of the must becomes unpredictable. To minimize these risks, it is essential to limit mixing between must fractions. Now, let's examine the key objectives associated with pressing. From a quality perspective, the priorities are to limit grape crushing, obtain clear and clean must, avoid the extraction of vegetal compounds, and maintain strict control over oxidation. From a productivity standpoint, the focus shifts to optimizing the duration and efficiency of each pressing cycle. And from a yield perspective, the aim is to maximize must extraction while avoiding excessive astringent tannins, release, or oxidative damage. In practice, the oenologist must adjust the pressing program and find the right compromise between these 3 objectives. quality, productivity, and yield in order to meet the overall production goals. Now, let's take a look at the principal two types of presses commonly used in winemaking: vertical press and pneumatic press. Before we begin, it is important to note that the press is one of the most expensive pieces of equipment in the winery, with prices typically ranging from about 20,000 Swiss francs to well over 100,000 Swiss francs, depending on size, technology, and level of automation. Traditional vertical presses are renowned for producing exceptionally clear must. The thickness and compactness of the solid material create a natural filtration layer, and because breaking up and remixing the pomace is difficult with this design, only a limited number of remixing steps can be carried out during the cycle. The main drawback of older vertical presses is their relatively high labor requirement, especially when the cage is not mobile. However, modern vertical presses have greatly improved this aspect through better ergonomics and partial automation, and they remain highly valued for the finesse and purity of the must they produce. Modern pneumatic presses represent a major technological advancement in winemaking. Their inflatable membrane allows for highly precise pressure control throughout the entire pressing cycle. The large draining surface and efficient drainage channels ensure rapid and gentle removal of the extracted juice. Because the breaking up of the pomace is automated, these systems significantly reduce labor requirements. However, compared with vertical presses, the higher number of remixing steps tends to produce must with a higher level of turbidity. Several configurations also provide excellent protection against oxidation, particularly through closed systems, inert gas options, or reduced oxygen designs. Here you can see two commercial examples that illustrate these technological features. In addition to the improvement in protection against oxidation, some models can automatically adjust pressing cycles based on the flow rate of pressing, improving both extraction efficiency and process reliability. Recent developments on the market have also led to noticeable improvements in cleaning systems and overall operational safety, making these presses easier to maintain and safe to use. When paired with an appropriately adapted pressing program, pneumatic presses can consistently deliver high-quality must with controlled extraction and minimal oxidative impact. In summary, each press type brings specific strengths. The role of the oenologist is, therefore, to tailor the pressing program to the grapes and to the wine style they aim to produce.